So while you're writing these down, it is in your best interest to replace that with u, and then remind yourself you have to multiply by u prime. So, or if you like theta, go ahead and replace these with theta and then theta prime. Because what will happen is if you have something other than just x, then you have to do the derivative of something other than just x. We're doing the derivative of x, but the derivative of x is 1. So it's in your best interest to use theta or u, so that you see that when you are doing the sine inverse of 2x, it's going to be 1 over 1, the square root of 1 minus 2x, the quantity squared, multiplied by 2. So it is in your best interest to consider writing those instead of, if you're writing these down for the first time, or if it's been a while since you wrote these down, to use u or theta. So I would write down on my paper d du is equal to 1 over the square root of 1 minus u squared, u prime. Make sure I put in the derivative of sine inverse. So the derivative of sine inverse of u is equal to. So you can do whatever, but I would recommend you do that. It will make it easier, especially when we start doing the derivatives here. So if I'm asked to find the derivative of the sine inverse of 2 theta, then f prime of theta for the first one is going to be 1 over the square root of 1 minus 2 theta squared times 2. How was that? Okay, so then I'm going to look at my next one, which is my tangent inverse, so number 2. So g of x is going to be equal to, it's going to be 2 is going to be the multiplier because I have a 2 as a multiplier. I come over here and I find the tangent. Tangent is 1 over 1 plus x squared. So this is going to be multiplied by 1 over 1 plus 3x squared squared. And then I still have to do the derivative of the 3x squared, so multiplied by 6x. So my final answer is going to be 12x over 1 plus, go ahead and distribute the squared in the denominator on the 3x squared, giving me 9x to the 4th. So that is my answer for g of x. My last one, which is h of x, so h of x prime, and that should be g prime. H of x prime is going to be 1/2 is still just the multiplier. And then I'm going to do the natural log derivative. This is the chain rule within the chain rule. So the derivative of the natural log of something is 1 over the secant inverse of 4 alpha. That should be alpha here. And then I'm going to do the derivative of the secant inverse of 4 alpha. So I'm going to go over here and find secant. That's going to be 1 over the absolute value. So this will be 1 over the absolute value of 4 theta multiplied by the square root of 4 alpha squared and minus 1. Then I still have to do the derivative of 4 alpha, so I get 4. My final answer in all of its glory, this 2 and that 4 will cancel themselves out, leaving me 2 over the secant inverse of 4 alpha multiplied by the absolute value of 4 alpha multiplied by the square root of 4 alpha, the quantity squared, minus 1. And there it is in all of its glory. How was that? Good morning. So going back up to 2, now with number 2, I have, let's start back up here. This is my u. So if I'm asked to, 2 is just a multiplier, so I'm asked to do du of the tangent inverse of u, then the 2 is just going to be a multiplier. The tangent inverse is 1 over 1 plus u squared, and then the derivative of u. So 2 being my multiplier here, this is the 1 over 1 plus u squared, and then this is my u prime. So when I did the multiplication here and cleaning this up algebraically, is I had to multiply this 2 times this 6x, which gives me the 12x squared. And then I have to square, so I'm going to take 3x squared and square it, which means my 3 is going to get squared, and then my x squared is going to be squared. And so I end up with 9x to the 4th. And that's where the 9x to the 4th came from. So that's the second one. Anything else? Now, let's take a look at these here. If we look at our derivatives, which we learned, hopefully you all learned last quarter. If you were in my class, you would have learned it. If you were in a different class, you may not have learned these. So here they are. And when we're doing the derivatives of these inverses, notice that I don't see sine or cosine in the derivatives. And the reason that is because when I'm doing the inverse of the function, of a trig function, it says I have the answer, what was the angle that produced it. So because I'm doing the inverse, the derivative of an inverse is I'm really chasing the angles that produce those answers. So that's why I don't have sine and cosine in the answers when I do the derivatives. So the derivatives of the inverses are just, you're chasing angles, basically. You're finding the angles that produce that. So you'll notice that for sine and cosine, sine and cosine here only have a difference between the two as being a negative or a positive. So it's either a negative or it's a positive. So those two are pretty much the same thing. One's positive and one is negative. We kind of expected cosine to be negative because when we do the derivative of cosine, then it's going to be the negative sine. So I expected that one to be negative. If I look at tangent and cotangent, one's positive and one's negative. So they're pretty much the same thing, but with a positive and negative difference. And then when I look at secant and cosecant, again, one's positive and one's negative. So they're pretty much the same thing, but one being positive and one being negative. What that means for us when we integrate these, because they're pretty much the same things, we're only going to, when we do the integrations, we're only going to use sine inverse, tangent inverse, and secant inverse. And then we adjust by putting the negatives when we need it. So when we see that form, du over the square root of a squared minus u squared, then if it's a negative or a positive, I use sine inverse. If I see du and I have a constant plus something that's not a constant, then I use the tangent. And if it's a negative, I just put a negative on the answer. So what I mean by that, if that would have been a negative du, then I'm just going to put a negative on my answer. If this would have been a negative outside, then I'm just going to put a negative on the outside. What I'm not going to do is I'm not going to write, if I see a negative du, I'm not going to write the sine, cosine inverse. I just use these three, and then I adjust for the negatives. So we only really have to look for these three type forms in which I have a constant squared. This is a constant squared. And then I have my argument or my variable squared. So I'm going to be looking for those patterns. So in other words, I'm going to be looking for something like 1 over 9 squared, or excuse me, 9 minus x squared. That may be a pattern I'd look for. Or I may be looking for a pattern, say, 16 minus 9x squared in the denominator. So I'm looking for squareds. Now notice for this one, the difference between these two isn't just because I'm using a 16 first, but the real difference is that this u would have been x. This u would have been 3x. So I am looking for a constant minus some number, the square root, or I'm looking for a constant plus some variable or argument squared, or I'm looking for that variable or argument and then the square root, like this form. So I'm looking for those three forms. Now, if those are the three forms I'm looking for, then I may have to do some manipulations to get those three forms. So let's go through some examples. So I'm going to do the first one, and then I want you all to do the second one. I am looking for that pattern. I am looking for a constant minus something squared underneath a square root. If I have that, then I know that it looks like that. That is the sine inverse. So if I'm looking for that pattern, this constant is a squared. That constant in this case happens to be a squared. Down here, a squared happens to be 9, which tells me that a is equal to 3. A squared gives me 1, so a is equal to 1. Now I'm just going to follow the pattern. This is going to be equal to, because it matches this pattern, it's going to be the sine inverse of x over a, the absolute value of a, which is 1. And then I don't have to do the plus c because it's a definite integration, so 0 to 3, square root of 3 over 2. But because my a is 1, I don't even need that part of it. It's just going to be the inverse, sine inverse of x. So this is going to be equal to, well, I'm going to get my unit circle out. I'm going to figure out where on the unit circle in which I have the inverse that is defined, that it gives me an answer of square root of 3 over 2. Now remember, we are in calculus, so we are only in radians. Do not answer any of this stuff in degrees. If you answer this stuff in degrees, your web work is not going to like you. So make sure if you're with your calculators, make sure your calculators are in degrees. So the square root of 3 over 2 is pi. So this is going to be pi over 3. And then minus the sine inverse of 0 is going to be 0. So my final answer is pi over 3. I'm going to take a moment because some of these in your homework are going to ask for you to give answers because they're going to be definites. So with definite integration, I'm going to just take a moment and talk about the domains of the inverses because this is going to be kind of important. Now, the domain of sine inverse is from negative pi halves to pi halves. The domain of tangent inverse is negative pi halves to pi halves, but I don't get to include the ends. And then we have the last one, which is the secant. The domain of the secant inverse, which is the reciprocal of cosine, is going to be from 0, so it's actually 0 is inclusive, from 0 to pi halves, union between pi halves and pi. Now the reason that's important is because if I look on my unit circle and I'm asked to evaluate on my unit circle I look at my unit circle and the angle that represents square root of 3 over 2 is pi thirds for sine, and the other place it's positive is 2 pi over 3. So it is tempting to write 2 pi over 3 here, but I don't get to because 2 pi over 3 is not part of this domain. So I don't get to include that. So pay attention to when you're doing this, where your inverses are defined. And the reason I'm telling you this, I'm taking the time to do this, is because if I were to ask to evaluate, I would have gone back to the evaluation of, say, negative square root of 3 over 2 to 0 of the same thing, 1 over the square root, was it square root? Yep, 1 minus x squared dx. Then this is going to be equal to the sine inverse. We know it's going to be the sine inverse of x, evaluated from negative square root of 3 over 2 to 0. That this is going to be the sine inverse of 0 minus the sine inverse of negative square root of 3 over 2. Well, the square root of 3 over 2, so this is going to be 0 minus negative square root of 3 over 2 is negative pi thirds. So the answer to this is also pi thirds. So that's why I took a moment to talk about where the inverses are defined, because you have to pay attention to, if you're doing the definite integral, what values you're actually going to be able to use. So with that said, do you have any questions with that first one I did and the example I did for the second one? Any kind of questions? So go ahead and do B since you have no questions. And remember, you're looking for those patterns. And if you have something other than 1 minus x squared underneath the square root, then you have to deal with that value. A is what we call it. So go ahead and do 1, and if you're, or B, do B. And if you have B and you've got it, go ahead and do C, please. So on B, this is going to be equal to the sine inverse of x over A, which is 3, the absolute value of 3, plus C. Now, because I'm using the positive 3, I can go ahead and take those absolute values off. And again, the reason that we're doing it is because when I have A squared is equal to 9, that means to get A squared, A could have been also negative 3, and A could have been positive 3. So the absolute value is there just to ensure that you're not choosing the negative, because to get A squared, it could have been positive 3 or negative 3. So you can put the absolute values on that 3 just to ensure it, but if you are choosing the positive, it is going to just be 3. So it's up to you whether or not you put that on there. Taking a look at C, we notice that this matches the tangent, where A squared is equal to 1, so A is equal to 1. I'm going to use 1 so that I don't have to worry about the absolute value part of it. Tangent inverse doesn't have an absolute value because the tangent can be negative numbers, so it doesn't have the absolute value. But anyways, this becomes the tangent inverse, 1 over 1, so that's just 1, so I'm not going to put that on there because it is 1 over A, is going to be the tangent inverse of x over A, or just x, evaluated from the square root of 3 to 1. So the tangent inverse of 1 minus the tangent inverse of the square root of 3. So the tangent inverse of 1 is pi over 4 minus the tangent inverse of square root of 3 is pi over 3. Having the same common denominator is I'm going to multiply this by 4 over 4. I'm going to multiply this by 3 over 3. And so I end up with 3 pi minus 4 pi over 12, which gives me negative pi over 12. And that's my final answer. How are we doing? Okay. So what about the next one? And I'm going to talk about E in a minute. What about the next one? What do we get for the next one? Which one does this match up to? Sine inverse, tangent inverse, or secant inverse? So we got pi over 4 for D. So let's go ahead and take a look at D. This matches the secant inverse because it's the absolute value. And so here, actually here, A squared is equal to 1. That means A is equal to 1. And so this is just going to be and it matches exactly the secant inverse. So this is the secant inverse. Again, I have 1 over A. A is 1, so I don't have to worry about that. So the secant inverse of x over A, or just x, evaluated from 1 to the square root of 2. So I'm going to do the secant inverse of the square root of 2 minus the secant inverse of 1. The secant inverse of the square root of 2, well, that happens when we're at pi over 4. So when I see the square root of 2, it's pi over 4. And then for secant to equal 1, remember secant is the reciprocal of cosine. So for the secant inverse to equal 1, that means I must have had the cosine to equal 1, and that means I have 0. So my final answer is pi over 4. How was that? How was C and D so far? How was C and D so far? As we take a look at E, what I have to do with E is I have to either think about use substitution here, which I would then say, I can do this one of two ways. Let U equal 4x squared, or 4x, excuse me. Let U equal 2x. That means du is equal to 1/2, u is equal to 2 dx, which gives me 1/2 du is equal to dx. So if I do that, then I've got a replacement for the dx. I have a replacement for this, but then I have to worry about that. And I can do it that way, absolutely. And if I do it that way, then I have to adjust for the u. So I'd have to say, okay, well, right now what I have is, let me erase this. So what I have is I have a replacement. So this can become 1/2. Du can be here. I have the square root of u squared minus 16, but I'm still missing this piece here. So to adjust for that piece, which is totally fine to do it this way, is I'm going to take this and solve for x. So I get 1/2 u is equal to x. And that means right here I'm going to have that replacement of 1/2 u, absolute value. And then it'll match what I want it to be. So this is going to be equal to 1/2 the integral of du. Well, 1/2 is a positive number, so I can take it out of the absolute value. So it's going to be 1/2 the absolute value of u, the square root of u squared minus 16. And then, because I have 1/2 times that, or in the denominator, this is going to be the same thing as 1/2. This will come into the numerator because I have a fraction with a fraction, so I have 2 du is equal to the absolute value of u, square root of u squared minus 16, which then gives me, those 2's will cancel, giving me just the integral of du, the absolute value of u, the square root of u squared minus 16. Now it matches the secant inverse. Here, a squared is equal to 16. That means a is equal to 4. So this integral is equal to 1 over the absolute value of a, which is 1/4. The secant inverse of u over 4, absolute value of 4 is still 4, plus c. But I don't have c, I have u, so I get 1/4 the secant inverse of u. We said u was 2x over 4 plus c. So this is equal to 1/4 the secant inverse of x over 2 plus c. That's one way of doing it. That will work every single time. It's not the way I would have probably done it myself, but that's one way of doing it. So let me expand out so you can see all the work that happened to that. I'm going to stop the recording for a minute and let you look at it, and then I'm going to show you an alternative way of doing E and why I probably would have done E that way. Okay, so let's take a look at E again. Now, with E, I'm going to do it slightly differently. In the fact with E, I see the denominator. I see that they both, underneath the square root, they both have a 4 that is common. So I'm just going to take and do this algebraically and rewrite this algebraically as the integral of dx, the absolute value of x, the square root, and each one of those terms underneath the square root have a 4, so I'm going to factor out a 4, leaving me x squared minus 4. And then because each one of those have that 4 that will factor out, then I can take the square root of 4. So I get the integral of dx over 2. So 2 comes out because of this. Square root of 4 is 2. The absolute value of x, the square root of x squared minus 4. So this is equal to 1/2 the integral of dx, the absolute value of x, the square root of x squared minus 4. And then a squared is equal to 4. That means a is equal to 2. So this is going to be 1/2 using the inverse for the tangent inverse of secant. So this is going to be 1/2 multiplied by 1 over a, which is 2. The absolute value of 2 is 2. The secant inverse of x over a, which is 2. Put the absolute values on there so you know where those are coming from. Plus c. And so I get 1/4 the secant inverse of x over 2 plus c. And I was able to do that one without doing the u substitution. And the only reason I was allowed to do that is because I have a 4 that's common in each one of these two. So I was able to factor that out and then take the square root of 4. If that would have been 9 and 16, I would not have been able to do that, and I would have had to do it with the u substitution. But because I see that there's a 4 common in both of them, I can go ahead and pull that 4 out. Is there any questions on that one? Any questions on that one? So let's take a look at G. So with G, I will have to do u substitution here, because what I'm looking for is I'm looking for an a squared plus a u squared. So I'm looking for that kind of pattern. And I notice it's not just x squared, it's 16x squared. So I know that if that's the pattern I'm looking for, a must be 5. But this u must be 4x. The reason I have to do that is because my coefficient, just like I did on E, and I'm skipping F, is that my coefficient on x is not just 1. So I have to say, well, u must be 4x. And then I'm going to have to do the u substitution. So du is equal to 4. I keep moving that 4 over. 4 dx. So 1/4 du is equal to dx. And so what I have is I have 1/4 du over 25 plus u squared. And then this matches the pattern of the tangent. So this is going to be equal to 1/4. The tangent is multiplied by 1 over 5, because it's 1 over a, so 1 over 5. The tangent inverse of u over the absolute over a, which is 5, plus c. But remember, we are not solving for u, or we're not using u. We have to go back and back substitute. So it's 1 over 20. The tangent inverse of u, which was 4x over 5, plus c. What kind of questions do you have for me on that one? This one. For this one, what you want to do is we're going to look at the fact that I have 75, 50, and 25 in the denominator. So I'm going to factor out 75 over. I'm going to factor out a 25 out of each one of those. So I have 25, and then I have 75 divided by 25 is 3, minus 50 divided by 25 is 2 theta, and then minus theta squared d theta. So, and this, I'm telling you, this is on the homework. So the first thing I'm going to do is factor out that 25 to see if I can start making it look like one of the patterns I am wanting it to look like. So then if I am trying to do that, then I'm gonna do this as the 75 over, take the square root of 25, which is 5. And then I have the square root of 3 minus 2 theta minus theta squared d theta. And so I'm just going to clean this up just a little bit. And 75, it is what, 15? No, what is that? How many times does 5 go into 75? 25 times? Is that right? 25 times? And then I have the square root of 3 minus 2 theta minus theta squared d theta. Now remember, what I want is I want a pattern that, because I see a square root, is I want this to either look like, in the square root, I want it to look like 1 over the absolute value of u, the square root of u squared minus a number. That's what I'm looking for. Or I'm looking for 1 over some number squared minus that all underneath the square root. Now, what I see is, I see that there's no theta here. Because there's no theta there, then I know I'm not going to be using that one. So what I'm going to try to do then is I'm going to try to make sure that it matches. So I'm going to rewrite the denominator to be, so 25 here. I could pull that out. I'm just going to wait for a minute. I'm going to rewrite this as 3 minus theta squared minus 2 theta d theta. Now I'm just going to work with what's underneath the square root part. So what's underneath the square root part is 3 minus. Now I want a number minus my u, or in this case it may be something other than just theta. So I'm going to factor out a negative, so it leaves me theta squared plus 2 theta. Now I need this to be, what I need is I need to be a number minus something squared. So that means I'm going to have to complete the square on this portion. So to complete the square on this portion, what I need to do is I have 3 minus theta squared plus 2 theta. To complete the square, I take the 2, divide by 1, and square it. So that's what I need to do to complete the square. But I can't arbitrarily just add that 1. I can't do that. I'm not allowed to just arbitrarily add that 1. Because if I just arbitrarily add this 1 right here, then I have changed the value of what's underneath that square root. What I have to do is I have to adjust for it. Now remember, if I were to distribute this negative through, what I've really done is I've subtracted 1. Because I've really subtracted 1, then I need to make sure that I add 1 to it. So what I have is 3 plus 1, which is adjust this 1, will adjust for the fact that I have theta squared plus 2 theta plus 1. So that adjusts for this, which is really a minus 1. And so what I really have is 4 minus theta plus 1, the quantity squared. So with that in mind, this is equal to 25. Actually, you know what? I'm going to take that 25 out. So 25, 1 over the square root of 4 minus something squared d theta. So now it does match the pattern in which I want, so I can find the derivative of that. So I'm going to stop and ask you, what kind of questions do you have for me so far? Then this is going to be equal to a is 2, u is theta plus 1. So following the pattern, this is the sine, so it's going to be 25 sine sine inverse of theta plus 1 divided by my a, which is 2, plus c. That's my final answer. And these are on the homework, so I just wanted to just go through the algebraic manipulation for you on this to make sure you've seen it. Is there any questions for me? What kind of questions?
I did have one question.
Okay.
So you added 1 to complete the square right there, right?
Here?
And so what allows, I'm a little confused on just like being able to recognize when you need to do that.
Okay, so we're looking for that pattern. The pattern that we are looking for, because I have these 3 choices here, right? Is I have something squared, a number squared, minus some function squared. So underneath the square root. I know I can't use this one because I have, see that function is outside of the square root, so I know it's not going to be that one, so it's the sine. So I need to have a number squared minus a function squared. So what I have is this. My previous step is this. And so I need to make that theta squared plus 2 theta be a perfect square. Because it needs to be something, has to be a number squared minus something else squared. Right now it's not a perfect square, which means that I can't write it as something squared like I did down here on the very bottom. Because I have to have a perfect square trinomial, then I have to complete the square up here. So let me just erase this part. Let me erase this part. I have to complete the square here to make it a perfect square trinomial. This is currently not a perfect square trinomial. This portion is not. So I have to make it a perfect square trinomial because I'm looking for a number squared minus something else squared. And this is not something squared yet. I have a squared, but then I also have the 2 theta. So I have to complete the square on that. So I have to make that a perfect square trinomial, which means the way I do that is I take whatever is attached to the b, or the, you know, if you're thinking about this is ax squared plus bx plus c, and then I'm going to take whatever is attached to my theta, whatever my linear term is, that coefficient on my linear term, and I'm going to take half of that, whatever that number is, divide it by 2 and square it, and that's what I end up adding to make that a perfect square trinomial. So that once it's a perfect square trinomial, which is here, it will factor into that, so it then has that pattern there, which is what I'm looking for. Did that answer your question?
Yeah, we're just trying to get it in the form of a squared minus or plus u squared.
Yes.
I get that. Yep.
Okay. Anything else? Because like I said, these are going to be on the homework, and I want to make sure you know how to do them before you do the homework. Anything else? All right, if you have no other questions, I will have office hours today between 12:30 and 2. So if you have questions, you can drop in. Otherwise, have a great weekend. Be safe. Don't lick the handles on the shopping carts, doorknobs, anything else. Don't lick it. Have a great weekend.